I'm Kelly Kavlich, and I will be discussing cooperative control, integrating humans and controls in a dynamic environment. But first, a little bit about myself. I was born and raised in Cresco, Iowa. I attended Iowa State and earned my BFA in Interior Design in 2006, at which time I moved to Des Moines and started working for Cooperative Architects. In 2010, I returned to Iowa State for my Master's in Architecture, which I completed this past spring. I am now continuing my education and working towards my PhD in HCI. I am continuously working for Keffer Overton, but I also work in the Community Design Lab at the Research Park. I am active in both competitive and recreation softball leagues, as well as the Triathlon Club. My most memorable experience was completing in Ironman Louisville in 2009. Through combining my education and work experience, I have identified a highly desirable yet controversial technology, building control. Building systems and automation combine to form the building controls. While early systems had some type of control, I will be referring to building controls in the sense of remote control from the system, and the ability for integration of automation control as well. Buildings account for 30 to 40% of energy use globally, and because humans spend approximately 90% of their lives indoors, building controls came about as a solution to reduce building energy usage and to improve upon the indoor conditions. As a result of building controls, energy usage can be reduced by 40% when using HVAC controls and 70% when lighting and HVAC controls are combined. Building controls also have improved indoor conditions that contribute to human productivity and increase morale and satisfaction. Decreased energy usage not only saves money for the building owner, but also reduces energy demand on the local energy generation plants, and CO2 emissions are reduced to affect the global share. Building controls include windows and doors, shading, lighting, heating, ventilating, and air cooling systems, electrical appliances, and fire and security. Building controls are identified in the programming phase of design and are integrated into a building based on a computer simulation. Building controls are designed to reduce energy demand and remove human error, such as remembering to set the temperature back when leaving or only responding when they are uncomfortable. The simulation inputs are based on deterministic methods such as schedules, environmental stimulus, physical stimulus, illuminance levels, averages, and set points. People and their interactions are also based on deterministic methods. That is, all dynamic conditions are not considered in simulations. Therefore, buildings are designed for perfect people, but perfect people don't exist. Human behavior and interactions have effects on a building's energy demand and indoor conditions. Understanding this, current trends and solutions for building controls are utilizing stochastic methods to account for the variability in an environment. Building controls are now able to learn and adjust for the occupancy and environmental conditions, creating intelligent buildings. In the U.S., an intelligent building is defined as one which provides a productive and cost-effective environment through optimization of its four basic elements, including structures, systems, services, and management, and the interrelationships between them. In the United Kingdom, the definition is one that creates an environment which maximizes the effectiveness of the building's occupants while at the same time enabling efficient management of resources with minimum lifetime cost of hardware and facilities. That is, the U.S. is focusing on building technology, while the U.K. is focusing on the users. Cultural differences can help account for the differences in focus. However, both countries continuously approach the design for intelligent buildings in the same way. They both start with the building system requirements and how the building system can be controlled. The control function is selected based on the system control options, then the controls are provided to the user, and the user is educated on how to operate the controls. If we are so concerned about occupant health, safety, and welfare, why are we starting with the building systems and not the user? The reason is that we, as humans, have too strong of self-interest to make a change to be more environmentally responsible. Hence the reason that humans have essentially been removed from building control. Reliability and durability of ERB are diminished from users because of their habits and motives. ERB doesn't address people's core values. DeYoung has categorized 4 areas of satisfaction that need to be achieved in order to attain ERB. They are competence, The system needs to be intuitive, and the user needs to be able to identify, understand, and solve the environmental problem. Frugality is the second category and includes care and conservation of the finite resources we take for granted on a daily basis. The third category is participation and includes direct involvement from the user, and a common social goal and attitude need to be adopted in order to obtain the goal. Luxury is the final category. ERP can be obtained when the method to achievement is inexpensive and readily available. Identifying humans have the greatest influence on environmental conditions and on a building's energy demand. Why not start with the users? My research is exploring the inverse design process by beginning with the users and first identifying what is important to the users. Next, deciding on how the control should function, followed by allowing the overall system to design which building system should react. To give an example of this idea, we have a room with several workers. However, one of these workers is hot. That person's desired action is to be cooler. The user utilizes an intuitive control panel that directly addresses their issue. In this case, the user can select from I'm really hot, I'm warm, I'm cold, and I'm really cold. In this case, the user selects I'm warm. Next, the system decides which way is best to cool this occupant. The system utilizes the ASHRAE Human Comfort Psychrometric chart that defines human comfort based on the combination of humidity, airspeed, and dry bulb temperature to bring the user's environmental conditions back into the comfort zone. This information is combined with other physical factors such as the other occupants, current conditions, trend conditions, and predictive conditions to decide which system should react. The system can choose between increased airspeed, cool the temperature, or reduce humidity to bring the conditions back into the comfort zone. The system also considers that no one else is hot, it will be an immediate action, and the external temperature will be cooling down as it is late in the day. Therefore, the system chooses to use increased airspeed to cool the occupant. Benefit of the system gives the control back to the user while allowing for any user to be that user. The system is intuitive for the user, allows for individualized control, and also control when desired. The system also allows for adaptation for any condition, flexibility for the future, and maintains energy efficiency. This concludes my current research. If there are any questions or comments, please feel free to email me. Thank you.